Hello, everyone. My name is Cameron Riddell, and I am the Associate Python Instructor with Don't Use This Code. Welcome all to our monthly Python Exchange call. The purpose of these calls is to help Python thrive within the National Lab System and scientific research sites that choose Python as a part of their work. Our goal is to provide additional resources for people who are using Python as part of their work and to help connect people together so we don't solve the same problem 15 different ways, so that we can share our approaches, our software, our efforts, and skill. Remember, these meetings are recorded, so if you have a question, please don't ask one that requires any proprietary knowledge. Please use your best judgment as these meetings and recordings are open to the public. While we took a break in February, we do hold these events monthly. To stay informed, please sign up for the Python Exchange mailing list. We promise to only email you regarding the Python Exchange. For anyone who hasn't been to one of our Python Exchanges before, I want to walk everyone through the standard structure for what we do here. In a moment, I'll introduce the host panelists and guest panelists. They'll tell you about themselves and what type of questions they're here to answer, and what types of discussions they're interested in having with fellow Python users within the DOE. Then we'll introduce our guest panelists who will share their presentation. We'll then have an open discussion amongst the host panelists and answer any of your questions that you have submitted via the Q&A widget on your sidebar. Let me start by introducing myself just a little bit more. My name is Cameron Riddell, and I don't work in the National Lab. I do, however, have an academic background, though not in the hard sciences as probably everyone else here does, but in psychology, where I studied human memory. I am a recently converted to industry programmer, where I've been working with James Powell and the rest of the team at Don't Use This Code to deliver many courses, trainings, and events such as this one. I am also our resident Python and Pandas expert, so feel free to ask me questions related to those topics. Now, let's have our host panelists introduce themselves. Dan Allen, can you tell us a little bit about yourself, your work, and what types of questions and discussion we should ask you?
Sure. I'm a physicist by training, working now in scientific software at National Synchrotron Light Source 2 at Brookhaven. I work mainly in the area of the Blue Sky software project for data acquisition and management. And I'm happy to answer questions about large-scale collaborations across the DOE and at our international peer facilities and how to cooperatively build things together. That's me.
Fantastic. And thank you for joining us today as one of our host panelists. Next up, we have Tom Caswell. Can you tell us a little bit about yourself, your work, and the types of questions we should ask you?
Hi, my name is Tom Caswell. I work with Dan at NSLS2, primarily on the Blue Sky project. In addition to that, I'm also the project lead for Matplotlib and a core contributor to H5Py. I'd be happy to talk about visualization, how to structure data analysis, and a more general discussion of how to design reusable scientific software to make lives better for working scientists.
Great. Thank you so much, Tom. Next up, we have Tanny. A little bit about yourself, your work, and the types of questions we should ask you.
Hello, everyone. My name is Tanny, and I am a postdoc at Lawrence Berkeley National Laboratory. I'm currently working on the project that is developing ML Exchange, which is an open source platform to develop or deploy machine learning algorithms. My expertise is in machine learning deployment in Python, but I also do a little bit of the development of user interfaces by using Dash. So I'll be happy to take questions about that. Thank you.
Great. Thank you so much, Tanny. Next up, we have Pete. Pete, can you tell us a little about yourself, your work, and the types of questions we should ask you?
Hi there, thanks. I'm Pete Jemian. I work at the Argonne National Laboratory at the Advanced Photon Source. I've been working in the area of scientific instrument controls for almost 3 decades now, doing a variety of scientific measurements using Python and other languages. I'm also member of the Nexus Scientific Data Format Advisory Committee. So if you have any questions about instrument controls, Epic software, or Nexus, give me a shout.
Great. Thank you so much, Pete. And last but certainly not least, we have Andy. Andy, can you tell us a little bit about yourself, your work, and the types of questions we should ask you?
Hi, thanks. My name's Andy Barber. I'm a beamline scientist at the CSX beamline at NSLS2. I'm technically a physical chemist. I'm an enthusiastic Python user, use a lot of different packages, but not so much developer. We rely heavily on Python to collect data and to do science, but I'm really interested in exploring how to sort of balance, large-scale development to make it work for everyday science. So.
Great. Thank you so much, Andy. All right. That is it for our host panelists. I think we have a great panel today, and I'm very excited for the discussion that we get into. Next up, I will introduce our guest panelists who have prepared some remarks today to share with us. Today, we are joined with Laurie Stephey, who is a scientific data architect in the Data and Analytics Services Group at NERSC. She started at NERSC as a postdoc working on Python optimization, targeted at Cori's Intel's KNL architecture for the Dark Energy Spectroscopic Experiment processing pipeline. And she now works on larger Python strategy and stewardship at NERSC with a focus on helping Python and data-intensive users be productive on NERSC systems. We are also joined by another guest panelist, Daniel Margala. He recently joined the Data and Analytics Services Group at NERSC to help specific scientific Python users at NERSC effectively use GPUs on the new Perlmutter system. Previously, as a postdoc in the NERSC Exascale Science Application Program, he worked with the Dark Energy Spectroscopic Instrument, DESI, to leverage GPUs in their data processing pipeline, which is implemented primarily in Python. So, without any further ado, I will hand the reins over to our guest panelists. Laurie Stephey, can you please take us away?
Sure. Can you all hear me?
Yes.
I'll assume yes. Unless I hear otherwise. So let me try to share my screen here. All right. So this talk will be a tag team between me and Daniel. So I will start and end. And our topic is to tell you about the current state of Python at NERSC in the era of Perlmutter, which is our kind of brand new system. So for anyone not familiar with NERSC, we'll give you a brief overview. We'll kind of explain to you how we suggest Python or users use Python at NERSC. Of course, they're free to do it in a lot of ways. We try to provide some best practices. We're collecting data on how our users are using Python on Cori, so we can give you some of our results there. Dan will talk then about commissioning our new system, Perlmutter, which is a GPU system, and the challenges we've faced. We'll talk about our strategy for procuring our next system after Perlmutter, which doesn't have a name, so it's just N10. And then we've kind of seeded some questions for discussion. We're just really thrilled that there's so many experts here, so really excited to hear your thoughts on some of our burning questions. Okay, so what is NERSC? NERSC stands for the National Energy Research Scientific Computing Center. We're kind of a workhorse compute center for the Department of Energy. We serve all 6 offices of science. We have more than 8,000 users. And one distinguishing characteristic from NERSC and the other sort of leadership class facilities, so that's Argonne and Oak Ridge, is that we have a much wider, more diverse set of users. So we're trying really hard to help all of these users be productive, although they have, very different kinds of use cases, different job sizes, software stacks. So our goal is to enable all of them. Our current production system is Cori, which is an Intel CPU system. We have both Haswell and KNL partitions. And Perlmutter is our new system, which is still technically in commissioning. We've only received the first partition. So, just to give you some sense of who we are, so the Python team is really myself, Dan, who's here, and Roland, who's not here, but I think a lot of you know him, and he's primarily responsible for our Jupyter installation. We're not going to cover Jupyter; it's just too much to talk about. So maybe at some point you can have Roland give you an overview of that. So a little more detail about Cori, our production system on the floor. It's aging. It was commissioned in 2016, but still is our current production system. So we have about 2,000 Intel Haswell nodes, and we have a much larger KNL partition, almost 10,000 of these. Anybody who's not super familiar with KNL is this many-core power-efficient architecture, but it's pretty difficult for Python users to take good advantage of it. It has kind of a strange memory hierarchy and also kind of a slow clock speed. So that's been a challenge. Cori has some satellite systems. So we had a small GPU cluster to help us prepare for Perlmutter. We've got 18 nodes, each with 8 NVIDIA V100s. And we've also got some special large memory nodes, which serve people in bioinformatics, especially given their very memory-intensive workloads. So Perlmutter is our current system. I think we're top 5 on the top 500 list for, a lot of people think maybe that's not that meaningful, but I'll just throw that out there. So as I said, this system is currently in commissioning. It will have 2 partitions. The first partition is our GPU partition, which arrived, last summer. So this is 1,500 nodes, each with 4 A100 GPUs. The second phase, which will arrive this summer, will be about 3,000 AMD Milan CPUs. So our experience so far has only been with this GPU partition. And most of our flops are in our GPU partition. So for users who really need a lot of compute power, they kind of, the GPU partition is where the flops are, so that it pushes them to kind of adapt their application to our hardware. Okay, so how do we help provide Python? How do we support it? So our philosophy is we try to empower people to be as productive as possible. Scientists want to spend time getting their science done. They don't want to be debugging their code or their super fun Python configuration. So we provide Anaconda-based installations. People can use the Conda tool to create their own custom environments, which our data show is very popular. I think when we last looked, about 80% of users were using custom environments. From our point of view, that's great because, the less we have to be in the loop, the better. It's for users to be able to install whatever they need is better for us and for them. Of course, we provide Jupyter. Jupyter is extremely popular. We have, thousands of Python users, and almost all of them are also Jupyter users. Another approach as we move forward with more complex Python stacks, especially GPU Python stacks, which introduce a lot of complexity. Daniel will discuss that some, but we'd like to lower the barrier to entry for containers. So I'm on the team that is working on deploying Podman on Perlmutter. So we hope to provide a place where users can build and run Podman containers directly on our system. So we hope that will help with Python productivity. Well, all productivity, but Python productivity for this audience. And as I said, finally, we're capturing data on how people use Python. So we can use that to make decisions on what we're providing. And of course, it helps us, show management. Python is important. I mean, I know we all believe that here, but it's a little different, I think, for our management. And of course, in designing our future system, it's important to know what our usage is. We'll discuss that a little bit too. I don't want to spend too much time on this, but in 2020, we deployed some infrastructure on our system to help track Python usage in a lot of detail. You can check out our SciPy paper and presentation from 2021. I guess I can include the link afterwards, but this gives you the details. But a short summary is we have kind of a special monitoring hook we insert via the environment variable Python path, and we use a special site customize then to, at the end of the interpreter, as it's wrapping up, we can compare a list of interesting modules that we've created with what the user has imported. And then if we have a match, we can generate records. So that's what we do. And we collect all of this data, so we kind of know how big was your job, where was it running, what other libraries were in your job. Actually, quite a lot of information. You can also go to our public dashboard, which is at the moment under construction. We kind of use this pipeline as sort of a testing framework. So I've been experimenting with some pretty new Dask EX, and it's mostly working. So anyway, you'll see some data missing, and that's why. But yeah, we're trying to make our data public. If anybody has questions about, which libraries are popular, very happy to talk about that. We're switching over our monitoring framework from syslog-based monitoring to LDMS-based monitoring. We're held up a little bit, but that's the goal, and that's why we don't yet have this running on Perlmutter, but that's, of course, very important to us that we start getting this data. These data are a little out of date, but I don't think they change a whole lot. These are from early 2021. And our data collection just shows us, what are people doing on our system. So you can see our top libraries are NumPy, multiprocessing, Matplotlib, SciPy, and IPy kernel. So from this, we have a good idea of what we need to support, now and on future systems. We have a lot of kind of what you might think of as heavy scientific computation happening in NumPy and SciPy. We have visualization, which seems like no matter what analysis or simulation work you're doing, you often want to produce visualization when you're done, and Matplotlib is, of course, very popular. IPy kernel, everyone needs to use it to use Jupyter, so you can think of that as a proxy for Jupyter. So you can see that's very popular. And of course, we have a lot of single node parallelization happening, maybe not directly in the user code, but in libraries that they're using, happening via multiprocessing. So this is helpful for us to know, and as I said, it will inform our asks for future systems. All right, and I will now turn it over to Dan.
Thanks, thanks, Laurie. So I'll talk about kind of how we're thinking about Python on our new Perlmutter GPU system. So I think one of the biggest challenges for this new system is actually enabling Python users to be productive on the GPU system. So most Python applications are not going to be able to leverage the GPUs just right out of the box. There are maybe a few exceptions like PyTorch or TensorFlow. So some of the machine learning and AI use cases, those really popular libraries already have a ton of developer support that are already enabling those software packages to work on GPUs. But a lot of the smaller scientific applications don't have some other community implementing or re-implementing their code on the GPU. So one of the biggest challenges is just, how do we enable users to use those GPUs? And so there's a number of libraries that we've been kind of experimenting with and recommending to users. And notably, some of those are like CuPy and the Rapids, as well as Numba and JAX as well. I've listed some here. Another thing that's been really helpful, I think, for users in the community is kind of this organization around common interfaces and API standards, like the CUDA array interface, which lets a user kind of mix and match some of these GPU-enabled libraries. They can, create an array on a GPU using one library and pass that to a different library, because those libraries all, agree on what the array interface should be for those GPU device arrays, as well as like the Python data API standard. So it's those are really great community efforts that we like to pay attention to and recommend and have our users also pay attention to those. Another big challenge commissioning a new system is just the rapidly changing software environment. We hope some of this stabilizes over the lifetime of the system. Some of this may also be just a lot of these GPU libraries and software framework stacks are kind of just newer, and we're still ironing out the details. The best way to kind of, mix and match all these different pieces and recommend them to various users who think of all sorts of creative ways of, setting up their environment. One thing that we found extremely useful that we use at NERSC is the Reframe HPC testing framework to kind of automate system checkout tests. So Laurie and I can write tests, like as a user, we want to just make sure that we can create a Conda environment, install MPI for Pi and CuPi, and run some basic things. And we can write a test for that other people can, when there's software operating system upgrades or other upgrades to the system during maintenances, they can just kind of run these test suite, and we get immediate feedback if something on the system changed that broke something that a user is relying on. That's another extremely useful for piece. And in the next slide, I'll give an example of why that's important. Yeah, so this is a slide that I presented at a user training event a couple months ago, where I was kind of giving an overview, a couple steps of how to set up an environment where they could use CuPi. And one of the most important things is loading the CUDA software module and then installing a version of CuPi that's compatible with that software module. So these are instructions that I gave 2 months ago. And then I went and revisited this recently, a few days ago. And now that doesn't work anymore. So this is extremely frustrating from a user's perspective, I think. I feel really bad when these sorts of things happen. So I guess it was decided that module, that software module on the system was renamed, instead of CUDA, it was CUDA Toolkit. And now even for some reason, there's multiple versions of that CUDA Toolkit module, but the one that existed 2 months ago is not even available anymore. So I'm not exactly sure why that is. Maybe it's just an oversight. But again, from a user perspective, it's kind of very frustrating. So that's one thing that we're working on trying to improve from our user experience. We can go to the next slide. So when I first joined NERSC as a postdoc, I spent a lot of my time working with one particular science application that uses NERSC. That's the Dark Energy Spectroscopic Instrument. It's a cosmology experiment. It's a 5-year astronomy survey. Then they're trying to build the largest 3-dimensional map of the universe. Use that map to study the statistical distribution of matter in the universe, and they can kind of figure out how much dark energy is in the universe and how it sort of changed over the universe's history. So I've been helping them port I guess I've mainly focused on one part of their data processing pipeline to use GPUs. So they've been NERSC users for a while, so they've spent a lot of time optimizing their data processing pipeline to leverage some of those systems that Laurie was talking about earlier, like the Knights Landing partition of Cori. But then moving it all over to GPUs is like another huge amount of, it could be a lot of work. But having libraries like CuPi, which kind of have a very similar API as like NumPy and SciPy, really makes it a lot easier for the science developer who they've already invested a lot of time and energy learning the functions that they need. And NumPy and SciPy, they're kind of like backbone of the scientific computing libraries. To be able to just use those same sort of functions on the GPU is, I think, really powerful. Similar with Numba, you being able to use Numba CUDA for kind of the just-in-time compilation stuff is also really useful. So I have a lot of experience kind of looking at an application that's been optimized for CPU and then porting that over to GPU. And kind of the most important thing is kind of doing this I think in an iterative process and being very strategic about figuring out which part of your application has the most potential for benefit improvement using the GPU. So you do that by like profiling your application and understanding where the bottlenecks are in the application. So I think this kind of iterative process of looking at the application, profiling it, coming up with ideas, implementing them and testing them is really important. And then, so the next thing that we're doing with this application on Perlmutter is scaling it out. So we want to test, like, can we take this application that now runs really well on a single GPU node and run it and use the full Perlmutter system, so all 1,500 nodes. So I spent some time kind of refactoring this application. It's a data parallel application because they can pretty much analyze, independent exposures of the night sky. Kind of, they don't need to be analyzed all together at once. They can be analyzed independently, so they can kind of run on different compute nodes. But we were able to kind of test this full-scale system and run a processing that they did recently on the CPU on the Cori system, where they used like 100,000 node hours. We were able to run that on the new Perlmutter GPU system in roughly 1,000 node hours. So it's a pretty significant speed up, and it allows the DESI collaboration to kind of turn around like a reprocessing of entire data sets much more quicker, which is very helpful for them to kind of test new algorithms for processing the data and even just making it available to their scientists. And yeah, there's a lot of details. So we can, if there are questions, we can talk about some of the details later. But yeah, we can move ahead. So kind of the task ahead for us, we don't have this kind of nice data monitoring enabled yet on the new system. So we'd like to get that up to see kind of, are people actually using these GPU libraries on Perlmutter. And then we're continually trying to expand our documentation and write examples of how to use these libraries and host training events as well. We also want to work with teams that are developing new libraries that enable Python applications on GPUs, especially ones that help users scale out to multiple nodes. Yeah, we're really interested in helping Python users kind of go beyond like single node applications and really take advantage of the unique environments that HPC systems provide.
Okay, so we have just commissioned, and in fact are still commissioning Perlmutter, but are already planning our next system, which seems a little crazy, but that's how it works. And we're, of course, the thing at the forefront of our minds is how can we support Python users on these future systems? We're seeing sort of, well, in CPU hardware, there is some increasing diversity, especially now with ARM CPUs. I think NVIDIA now has their Grace Hopper ARM-based CPU. Of course, we still have traditional technologies like Power 9. So how well is Python supported on those? So we're trying to get access to some test systems. I think we're going to check out the NSF system Chameleon. Try maybe Summit for Power 9, just to get some sense of, how usable is Python. We'll use the DESI code that Daniel was working on as kind of a good litmus test, I think, because it uses quite a few libraries and it's a real user use case. The trend in accelerators has been diversifying. There's now NVIDIA, AMD, and GPU or Intel GPUs, and they're all reasonably different in terms of programming environment. So for Python, they have a very good ecosystem now on NVIDIA hardware, but there is some vendor lock-in. AMD has some minimal GPU support now, like things like Numba have a backend that will run on AMD hardware. I don't know what the situation is for Intel. They have a one API. Maybe somebody here knows better than we do. But our concern is if we were to buy a system with some of these more novel architectures, like how usable will it be for Python users? We want to avoid a situation where every time we buy a new machine every 5 years, people have to throw away their code and rewrite it, which no one wants to do. That's a huge lift for a lot of our users. So, our concern is how can we try to avoid that or at least mitigate it. So the stated mission need of NERSC 10, which is the future system, is to enable complex workflows. And by that, we mean, more than just kind of a traditional 1,000-node job where you have maybe MPI, coordinating your work, and then after 30 minutes of computation, you can write out your files to the file system, and that's it. But instead now we're seeing a lot of more complex use cases, especially from experimental and observational facilities where they may have data transfer steps, pre-processing, compute. May need additional jobs depending on the results of the first set of jobs. So we have these kind of complex DAG structures, and we also have web services or some kind of centralized place then for the results that the users want to update. So user requirements are growing in complexity, and we want to make sure we can support those going forward. So that's the stated mission need. Of course, there's this kind of tension, though, between how usable this system might be, how productive it is for our users, and how much performance we can kind of squeeze out of it. So we have these really fast, amazing accelerators. You could take FPGAs as the extreme example, but they're difficult for users to work with. So we're kind of, I guess, working on that right now in the design team. So we know this new system can't do everything, but our concern here is to make sure that in 2025 our Python users' needs are met. Those top 5 libraries that we mentioned, are they going to be able to run on all of the CPU and maybe accelerator hardware that we purchase for our system? So wrapping up, our trusty Python team, Daniel and me and Roland, have been working really hard to enable our growing user base to be productive on our systems. It kind of remains to be seen how much Python users will like Perlmutter. Once we can get some data, we'll have a better sense of what people are doing there. When our CPU partition is ready, we'll be able to take a look and see, how many people are running on CPU versus GPU. And yeah, we're working now on the design process for our next system. So. Okay, so this is the part then where we wanted to see these questions and hopefully get feedback from all of the experts here in the audience. Well, I'll read them all and maybe we can kind of go through one by one. But the first one is a question of scale. So Daniel mentioned a lot of our users are struggling to run at scale. So we see in our data that most of our jobs are single node jobs, despite having 10,000 nodes on our system. So our hypothesis is that it's difficult for users to scale. That it's kind of, at least anecdotally, what I see in answering user tickets and helping them with frameworks like MPI for Pi or Dask. So we're wondering, if you all have any ideas about how we can try to make it easier for Python users to scale. The second one is, of course, we already mentioned this question of different architectures. For our next system, if for hypothetically we purchase a system with AMD GPUs, are users looking at adding just a lot of if-else branching into their codes, depending on the architecture? I know that the array interface goes a long way in helping to kind of unify the syntax, but the backends may be different enough. So that's kind of an open question. In a perfect world, it would be great if, one Python program could run on any system, any hardware without any modifications, but I don't think we're there. And then finally, I don't know if this is a situation that any of you all have faced, but, how can you convey the value of Python and Python users in HPC to management and decision makers, especially in the context of our next system? So Anyway, that's all. So we'll thank you all for your attention and for listening. And yeah, I hope we can have some discussion.
Yeah, thank you so much for the fantastic talk here today. I'll start off with opening those discussion questions to our host panelists. So host panelists, do you have any comments about maybe your own experiences trying to get users to adopt a new framework or anything of that nature relating to these discussion points?
In the spirit of James and phrasing things in provocative ways, I wonder if a different way to phrase the how do we get Python users to scale up is how do we make sure the technologies and techniques you use on a supercomputer will scale down to a single multi-core machine that a user's more likely to have access to so that they can work on using these tools at home before they come to the big system.
Very great point. So Laurie, are there any plans or are there any ways that you can think of that some of these libraries might be leveraged at home in a way that I can just write code locally at home and then once I log into the server, just port my code over and it runs in parallel?
Yeah, so for the parallelization frameworks that I'm aware of are multiprocessing, which works within a single node, and I think users can test that on their own laptop without much trouble. MPI for Pi, which also I think can be tested on a laptop if they have more than one core. And DESC, which in theory will work on the user's laptop, but I think the setup, at least just the implementation details, are different enough that maybe it's harder for them to test the same stack. But yeah, Thomas, do you have any thoughts about, how we could make that easier or more seamless for people?
Unfortunately, no. I was just trying to fill in for James and asking provocative questions.
Sure.
Fantastic, yeah. Oh yeah, no, not to worry. I mean, right, if these weren't good discussion questions to ask, then there would be a simple, easy answer to them, and there would be no point in asking them. So thank you for sharing your thoughts. Host panelists, any other thoughts on how to try and get Python users to running up at maybe a larger scale than what they're used to?
So I can't really add how to make that happen, but I can echo Tom's point because I've been there myself, and I've often not sure how many resources to use at once and what happens when I use too many or I've done something kind of silly. So I think a lot of it is just fear from the user's part that they don't want to damage your machine. And so guidelines on like helping people understand what is and isn't okay, like maybe helpful.
Yeah, definitely. I've been on that end of being a user and you're like, I don't know what I can do and not break it. And I definitely don't want that email from the system administrator yelling at me because I used up too many resources or something of that nature. So Laurie and Daniel, are there any types of those guidelines in place or resources resources available to users that they can just kind of peruse through easily and see kind of the nuts and bolts of the shoulds and shouldn'ts?
It's a little bit funny that you say that because we have a lot of kind of policies in place that sort of will rein you in automatically. And so you have to work pretty hard to actually break something. It does happen every now and then, especially with shared file systems. If you're doing kind of a, heavy I/O work, you can kind of use up all of the file system resources. I think that's probably the most common kind of resource issue we've seen. But very few users actually manage to reach the level where they are being, chided by a sysadmin, and usually they're very nice about it.
Yeah.
But how could we communicate to users like, do whatever you want to do, and if it's a problem, like we'll let you know. But
Yeah. Sometimes I find it's that the users just don't know what they can do to begin with, right? They don't know that they can work on more than one node, or if they have a vague idea of that they can do that, they don't know how to implement that within their own Python code that they've already written and, like Tom said, have tested at home. So I guess a good question to ask is, how would one go about scaling up their code, even if they have the know-how to? What types of changes are you looking for within a given script?
I think it kind of depends on the application. So the most traditional way is MPI for Pi, which for a beginner is tough to learn. You have to have this whole new way of thinking about parallel code. So I forget where that library is on our list. It's not in the top 10, I don't think. Yeah, it's down here. So we're not seeing a lot of uptake. Yeah, Dask I think is increasingly popular. You don't have to think as much about parallelism. You just have to think about tasks. How can you divide your problem up into some kind of smaller pieces, and Dask sort of handles it. Dan, having done a lot of the parallelization for DESI, do you want to add anything?
Yeah, I mean, DESI is kind of a special case because they have, been using HPC for a while, and they've gone this route of using MPI for Pi. Although some steps in their pipeline do use multiprocessing, I think they do though. Like they prefer to work on their laptop and then run code like at scale on the system. But so they do have some strict requirements. Like their stuff has to be able to run on a laptop, even if it's not super efficient on their laptop. Another thing I've noticed, like helping out other science teams in like sort of these hackathon events, is that some users like, so I've focused mostly on helping them like move code to the GPU, so like they get a huge boost, like translating like NumPy to CuPy. But then once they do that, they're like, okay, what next? Like, how do I use like multiple processes at a time? And sometimes like I've tried to introduce like MPI for Pi in like a 1 day or 2 day event type of thing, and it is a lot. It's a different way of thinking, especially if you're used to using like the multiprocessing library, which is in the Python standard library. Like MPI for Pi is kind of a different way of doing parallelism in Python that requires a lot to think about for someone that is not necessarily a software developer. They're a scientist and they want to do science. They don't necessarily want to like have to learn another way to program or think about their program. So I think that is a challenge. So.
Yeah, and we see that challenge a lot within kind of the academic sphere. At least I used to work at the National Institutes of Health. We had a very similar issue where we had some in-house architecture that people would use a lot, but maybe they wanted to do it in their own language. Like a lot of people were much more comfortable with MATLAB. And then they started rolling out this Python interface, and more people just began picking it up. And I actually do have a follow-up question off of that for both of you, Laurie and Daniel. I'm just curious, why Python? How would you settle on a Python framework for all of this and not use some other language, maybe a shiny, newer one?
Well, DESI's their calculation was, compute resources are no longer the limiting factor for them. It's developer resources. And so that's why they were willing to consider Python and not like a more traditional C++ or Fortran implementation. They were making this decision, I don't know, 5 or 10 years ago when Python was kind of the, I don't know, most popular, very usable language. If they were doing it today, maybe they would have chosen Julia or something. Do you want to add anything?
No, I saw Daniel shake his head. You don't think so?
I think Julia has a few more years still.
Yeah.
It's not super mature just yet, is it?
Right.
Right. And I actually, when I was a graduate student, I worked on a similar experiment to DESI. That was its predecessor, and that pipeline was actually implemented in IDL. So Python was kind of a leap forward in some sense.
Wow,
Yeah,
that's
at
very
least
neat.
from the users that we interact with, a lot of them are not HPC experts. You know, they don't want to be programming at the really low level. I mean, I'm preaching to the choir here since we all love Python, but you know, they want a readable, productive framework, and I think that's how a lot of people end up with Python. They're a huge fraction of our HPC users and growing, at least in the years that we've been monitoring. So
Yeah,
Yeah.
I suspect a lot of Python users are actually, they don't have one application. They actually have many applications. They use Python to analyze like the different data sets that they encounter, like a different data set every week or something like that. And they're writing scripts to analyze these data sets and come up with new ideas to do new experiments and collect different kinds of data sets. It's kind of different than building like one large simulation that's like one large application, and then you just need to run that for a really long time. So it's a little different than like maybe traditional HPC use cases.
Yeah, and I think that's a great kind of interface that you all are rolling out with the kind of the Jupyter interface, since that's more akin to kind of some just one-off, maybe not, you know, super fast, but relatively quick, just, you know, check, see if it works. I'm curious, did you decide from the get-go to roll out a Jupyter environment or interface alongside this HPC?
Roland would be the right person to tell you, but I think we've had Python on our systems now for, I don't know, 10 years or something. The story that he tells is that the first users who requested Python were told no. So I'm glad we've come a long way since then. But I think he started deploying Jupyter in earnest maybe about 5 years ago. So it's been a while, but I think just kind of Python. The Python users have been around a little bit longer.
Yeah, and I mean, I wish Roland was here to share with us, but I'm sure you've gotten a much broader audience since you introduced kind of the Jupyter ecosystem into this. I find with a lot of individuals who are maybe kind of new to Python, it's just an easy interface to work with to do some quick analyses. But I do want to get to this next discussion point about Python libraries supporting different architectures with the same interface. I am curious from our host panelists if you've seen any other Python packages out there that might have started as a diverse array of packages and maybe come together under some umbrella package that you might have worked with.
Oops, sorry.
Oh yeah, go ahead. Go ahead.
Yeah, I was just, actually, I was very interested, I think, in this point of the discussion as well, because in the group that I'm currently involved with, we are trying to do something quite similar in the terms of we have been thinking about deploying containers in order to make Python codes a little bit more portable. But as we have been testing recently, it seems like it's not as portable as we were expecting, especially for ARM-based architectures. We're currently using Docker, and I was just really curious about what your experience has been so far, what are the technologies for container deployment that you have, looked into so far, and have you encountered as well this, I believe that because of this discussion point being here is because you have encountered probably like a similar problem that we did.
Yeah, so I think containers are great. We're working hard to enable people to be able to use Podman. So it's very much like Docker, and this would allow users to actually build on our hardware and then run. So these would be unprivileged namespace containers. So yes, that is something we're working to enable. Regarding portability, yeah, it's difficult because I think for a lot of containers, you're building on like a Power 9 base image or an x86 image, and you won't be able to use the same one on different architectures. I think now there are some cross-architecture builds. I think they're kind of new, and I haven't tested them myself yet. So I think that's coming, and I think that will help. But like for the Python piece, the container build part won't help if there's no backend, like on an AMD GPU, for example. So I think that's a concern, at least for us. If we had an AMD GPU system come tomorrow, how well would the Python workloads be able to use it? Are any of you running on these kinds of accelerators, the AMD GPUs?
Were you running on NVIDIA GPUs? But the major idea is that we would like to deploy in many different locations, including NERSC. And I think that that is something that we have been discussing about. I think at some point we will probably explore more Kubernetes as well in order to make this portability a little bit easier. And I think that what we're trying to do as well, at least for our current implementation, is just to kind of like have a setup as well for kind of like guidelines in how to build up our images in order to make this portability happen a little bit easily among at least the host computing resources that we're going to have available within our platform. But yeah, those are like some few thoughts. And I think it's a very interesting topic because I do believe that containers are probably the way to go as well in the future. Once we will have a little bit more support, I think that in this case, most of the problems that we have faced have been basically just because of how we could say like recently ARM-based architecture has ARM-based architecture has become a little bit more popular since the release of the M1 chips. And I think for that reason is that we're just a little bit, so the M1 chips were recently released, and I think that some few Python packages still have to kind of like catch up. But I think that they are slowly catching up. But yeah, it's just an interesting thought, and it's something that I was just like really curious about. So thank you.
Yeah, thanks for sharing that and giving us some insight into what your goals are.
Definitely. Host panelists, is there anyone else working with similar types of problems or infrastructure?
I guess I was going to ask, other than, so I acknowledge the GPUs not having a backend is obviously a major problem, but with the different CPU architectures, has there been major portability issues other than binaries not being built?
I think we're kind of in the middle of figuring that out.
Okay.
So hopefully not, but our goal is to try to get access to all of the kind of ARM and Power 9 and just kind of check.
Right.
I know, yeah, there are some packages maybe that aren't quite up to date. Have any of you run into any gotchas?
I'm just saying on the library side for both Matplotlib and H5Py, we've pre-type build has been a problem, but that's been fixed. Build a really old version. But other than that, things have basically just built.
On ARM?
On ARM and Power.
Great.
And I know we have AIX users from Matplotlib too, because every so often they report weird build issues to us.
Yeah, I'm glad to hear that.
But the issues almost always are just like we're invoking make wrong, or we're invoking GCC without the right flags. And once because we used a flag that doesn't exist on their platform.
Makes
Thanks.
sense.
Yeah. Any of the other communities you work with, do you know if they've run into any problems, or at least for Matplotlib and H5Py, it's been relatively smooth sailing?
I mean, people are unhappy we don't have wheels up for every version for their platforms, but I think every platform that we've had has built. Just we don't provide the binaries. I know Conda 4 just has a big effort to do ARM 64, and they've built most of it there.
Great. Well, that's
And
encouraging.
Yeah. Tom, you brought up an interesting point about Conda, and I know Laurie from your part of the talk, actually might have been Daniel, but you mentioned that you let your users install kind of arbitrary Conda environments. I'm curious about how you go about managing the packages that they install. Have you set up your own kind of Conda channel for those things, or do you just let them install from the Conda repos? themselves?
Yeah, today we don't have our own channels, so most of their stuff is coming down from default or Conda Forge. We have kind of talked about it. There are a few things like MPI4Pi and H5Pi that like we kind of could need to be built specifically, for our systems. I think it gets a little dicey because some of that is using proprietary Cray software, so I think it would need to be kind of an internal situation. So I think that's something we could consider. But yeah, today everybody gets almost everything from Conda or Conda Forge, and then they just build these few special packages manually.
I would go that route. Consider it very carefully. We tried maintaining.
What do you mean, the Conda channel?
Yeah, we tried maintaining our own for a while, and it was way more work than we expected. And
really, can you like go into any detail? Like, what were the headaches?
Just typical packaging problems. That it's just details on details on details, and if you've got something pinned wrong, something upstream moves and your pins don't move, or one thing that got us is, so a nice thing Conda will do is that they will patch their metadata after it's built. Like if they discover after the fact that like something's incompatible, they'll just go and patch the metadata and say you can't install these two together. But if you're not keeping track of that, you can get out of sync with that. Anything you mirror yourself, you have to make sure you promptly rebuild and sync when they do, because then if you do install with a mix, you'll get like really weird pinbacks based on what's available on which channel, and it turns into a quagmire quickly.
So did you abandon that?
Yeah, we've mostly moved to just use the custom stuff we wanted to build. We've just put it on Conda Forge, and now we use that as the ground truth for our packaging for what we deploy to the floor. And if Maxim is still here, he's the one who did most of that. Oh, we lost Maxim. But on the other hand, if I can also see the case being, I don't mean to say it's impossible. Just be aware, like you're signing up for a fair amount of work.
So I have a question from the user's perspective. So with these Conda environments, do you allow the users to just install it for themselves to use? Or can they install it in their project directory so that everybody within the project can utilize the same Conda environment?
Both. And we have a lot of collaborations who do the second thing you mentioned. So they have a shared project directory that everyone can access, and then someone from the collaboration will install their own Conda installation and then populate it with the packages that they want. So yeah, a lot of the bigger collaborations go that route because they like to have a uniform software stack. DESI is one. But we also provide just a central Conda installation people can get via a module, and then they can use that to make whatever custom environment they want. And we wouldn't stop anybody from installing their own too, so they can do kind of whatever they want.
Cool, thanks.
Yeah, that being said, the users are good at doing a lot of different things and often tie themselves into knots using like Conda environments, but then also like pip install with the -- user, and Python is looking in all these places for packages, and often users like, I installed this version but it's not there, I have this other version. And I think we spend a lot of time helping users kind of like untangle their environment.
I've done that myself actually.
Yeah.
So I guess, are there any tools out there for people sort of, I guess, at my level, not your level, to quickly troubleshoot that issue for themselves?
Well, I mean, I learn a lot, like trying to understand those issues. So I learn how to, all the environment variables that Python uses to find packages, and these different tricks for like listing all of the directories that Python is going to search, or special like how Conda works. So I don't know what the right answer is, but I don't think you're not alone.
No, not at
Oh,
all.
yeah. Okay, it sounds like everyone here has had some type of issue with Kona environments at some point, right? And I think what
Yes.
Daniel said is the the most ideal, or not ideal, but the most common case where I conda installed something and then I pip installed something else, or maybe I downgraded it with a pip install, and then I try and conda install something else, and the whole environment's just broken.
Yeah,
Yes.
I think it's hard. Like, I also understand like users are looking at like installation instructions for like a particular science package that someone wrote to get something working. Because again, they're not software developers or technical documentation writers. They're trying to get science done. So they're, doing what they need to do to get their results. But then trying to, like, when other people go and copy that, it doesn't necessarily, you can't translate it directly to the different system or something. I think the best thing that we can do is try to have good documentation, and provide good, examples and training for users. But it's a lot of work also to keep that stuff up to date. Like, we're a pretty small team for all of these users.
Yes.
Yeah. One of the practices that I've found that helped me personally manage some of the packaging in my Conda environments, is to actually just always use an environment YAML file. And if I ever want to add a new package or something like that, I just put it into the YAML file, and then I update the environment from that YAML file. And that way I'm not really doing anything one-off from the command line, and then I don't really get anything out of sync.
Yeah, that's a
But
good idea. I guess in my own work, I try to avoid pip wherever possible. And I think even Conda says if you're going to use pip, do it after all of your other Conda installations.
yeah,
Because it seems like once you start mixing the two, it's easy to have things go wrong. I also always use pip inside a Conda environment and not outside. So don't use the -- user. And then I think like the number one cause of problems is people who have put things in their dot files, so like a bash RC or a customized startup file that might have been helpful at one point, and then they've forgotten about it. And then it seems like that often will come back and break something later. So I try to avoid customizations myself. I don't know if that's helpful for anyone else.
yeah, no, I can relate, and it looks like Tom and Andy both relate as well. I had some issues installing Jupyter from a Kona environment, and I realized I had some global Jupyter config file that it was reading from, and at the time I was using the Jupyter plugins, like the original Jupyter Notebook plugins, and every time I would start up, I would just get a list of error messages saying can't find this, can't find that, and I'm like, why are you even trying to find it? But I definitely agree. Never use the user. Always install it straight into the environment as a good best practice.
Can you make?
Yeah. Oh yeah, Tom.
Can you make the location where pip-user installs read-only for all of your users in their home directories?
So we do actually set that location for historical reasons. And so it's not read only. It's like a .local system name kind of path. But the issue is in trying to help, we might make it worse.
Yeah. Always the best intentions, right?
Yeah. The other difficulty is some of our other colleagues sometimes do suggest the pip-user approach, and then we kind of get stuck trying to reconcile all these different strategies.
Yeah. Okay. So before we go too far off on this Anaconda tangent, I do want to get to the third discussion question that you all had. Is what strategies do people use to most effectively communicate the value of Python and HPC to management and decision makers? So our host panelists, have you ever had to convey, right, the reasoning why you need all this heavy duty code maybe to someone higher up who just doesn't get it? No? If so, or if not, I'm curious, Laurie, how are you all currently approaching that? Or what's your current advice for users trying to do that?
Well, our users are, in a lot of cases, Python users. Especially our users are heavily grad students and postdocs. Many of them are Python users in some form. So I don't think there's any trouble there. I think that it's just, like I said, this 10 years ago when someone asked for Python at NERSC and was told no, I think the idea was like, oh, that's not a real HPC language. And so things have changed a lot since then, but maybe we're still trying to convey this kind of change to some management or decision makers who have this more kind of old-fashioned idea. Do any of you ever run into that, or are people surprised that your users or that you are doing your heavy computation in Python?
At least personally, from kind of like a machine learning perspective, it's usually straightforward for these type of users to utilize these resources, since especially the analysis of deep learning algorithms in like a regular computer will take like weeks. So I think that, in this line of work, I think that users mostly look for this type of resources. I think the question will be more of, do they have access to it, or do they know about it? I think during my onboarding process with the lab, they did a very good job at telling me about all these resources that I had. I do wonder if maybe some other onboarding processes within probably other labs or something do discuss those probably in one of those training courses that we usually take, but I wonder if they really make like an impactful introduction to what type of resources they have. And as you mentioned as well before, because I think that I was also at the very beginning a user that was also concerned about breaking things. And I think it is quite a big statement as well, just to say the resources are there, use as many as you need. And we will tell you what's enough. But yeah, I think that, at least from my perspective, but as well as a postdoc and as a machine learning user, we don't usually have to convey the idea that HPC resources are very valuable, since usually these research community do accept those and they are very interested in using them. It's more about, do they know that they have these resources available to them? So I think that that's kind of at least my perspective on this matter.
Thank you.
That's some great insight. Thank you so much, Tanny. And this does bring us to the end of our time. Then we will go ahead and adjourn. We will be meeting again next month on the last Wednesday of the month. If you are not signed up for our newsletter, I encourage you to sign up for our newsletter, and that way you can stay up to date with all the happenings and upcoming events that we have to offer. And again, my name is Cameron Riddell, and I will see you all next time. Thank you so much to our host panelists and our guest panelists today.
Thank you.